It's a great honour to be here, and I'm looking forward to discussing things further with people during the breaks. I've got 40 minutes this morning, so I've been told, to explain the meaning of life, I guess, in 5 words or less. I'm going to be rushing through this fairly quickly, so if you would, want to ask questions, we won't really have time this morning. But this afternoon, I'm hoping to allow a little bit of time in my talk to be able to field questions, or as I said, you can chat to me during the breaks. This is, some of you may have seen this, Darren Corman's work on Canadian net farm income. I realise this is a different country, but I think you'll agree that the statistics are fairly similar to what's happening here in the United States. I don't have a pointer either, sorry, unless, no, that's not one. Okay, I do have those things in my bag. I should have brought them up here. But anyway, if you have a look, this goes from 1926 to 2016, this 80-year period here. If you look right up to about 1970, you'll see the blue line, or the blue area, is actually the gross revenue earned from agricultural production. So it goes up and down depending on the seasons, on commodity prices and all that sort of thing. We're aware of all these changes that happen to gross revenue over time. The green line is net farm income. It's your net revenue back on the farm. And you'll see that up to about 1970, when seasons were good and commodity prices were good and gross revenue went up, net farm income went up as well. And then when things went down, net farm income went down. And that's the kind of relationship between gross and net that we would like to see. But then after about 1970, those two lines start going in different directions. Gross farm income, or gross revenue, continued to go up. And it is still going up. But the green line, your net farm income, has been going down. And in fact, in 2006, which I figure was probably the same thing here, it's in the red because of the low corn prices in that year. So what is going on? Why are these two lines separating and going in different directions? Well, if we have a look in a little more detail at this data, and I have a link to this paper if anyone would like it, it's very, very insightful. In the 32-year period from 1985 to 2016, that is agribusiness, like the input suppliers, the people who supply you with your seeds and your fertilisers and your tractors, and the lenders and all those, the service providers, received $1.32 trillion of the $1.35 trillion of revenue earned through agricultural production. In other words, 98%. So 98% of what was earned in the agricultural industry went to input providers. And today the majority of Canadian farmers are supported by off-farm income, taxpayer-funded support schemes, asset sales and borrowed money. Does that sound familiar? Well, and farm debt in Canada is at a record high, just under $100 billion, and farm debt in the USA is also at a record high. And we down under in Australia, we can't point the finger at what you guys are doing up here because we have exactly the same trend happening in Australia. So that figure there, the green line is our revenue and or the gross value of farm production, and the red line is debt. So debt is overtaking our farm production. And if we just look in something that I'm a little bit more familiar with, we grow a lot of wheat in Australia, and our average wheat yield doubled between 1980 and 2000, and in that same period, farmers' profits halved. So I'm not pointing the finger at the United States by any means. Now, we're repeatedly told that we need to produce more to get out of this mess, but it's actually not about maximising yield. So it's not about maximising yield, it's actually about optimising profit. And we have to regenerate the resource base, and we want to be producing nourishing food. So I just want to dwell on that for a moment. We're linking soil health and human health. Lloyd Noble, who was the founder of the Noble Foundation, said that no civilization has outlived the usefulness of its soils. Well, I want to add to that no civilization has outlived the health of its citizens. And if you think that's a grand statement, you really need to look at the health situation here in the United States. At the moment, United States citizens spend twice as much on health care than people in any other country in the world, but your health and life expectancy actually rates 17th on the list of other countries. Cardiovascular disease, cancer and Alzheimer's are the 3 leading causes of death in this country, and all are nutritionally related. All can be reversed with a change in the diet. 46% of children in the United States now suffer some kind of chronic disease, And those of you who have children or grandchildren will understand exactly what I'm talking about. The childhood illnesses are scary and they are increasing exponentially. They're not infectious diseases. They're all to do with the food. There's been a dramatic increase in the incidence of over 80 autoimmune disorders in recent years. That's where the body's immunity is not functioning effectively. They currently affect 1 in 6 Americans, and the numbers are growing daily. It's going to be, 1 in 5, 1 in 4, 1 in 3, 1 in 2 very, very quickly. So what are autoimmune diseases? They're non-infectious diseases that include things like diabetes, cancer, autism, Alzheimer's, dementia, lupus, multiple sclerosis, inflammatory bowel disease, rheumatoid arthritis, etc., etc. They're all autoimmune. They're all the body dysfunction within the body. Most of these, if not all of them, can be cured with fecal transplants, which indicates that it's something out of balance in the gut microbiome. They're not infectious diseases. They cost the United States $1.1 trillion a year, but that's just looking at it from an economic perspective. They cost a huge amount in heartache and grieving and emotional upsets within families, especially when these diseases occur in children. So in the early 1900s, Professor William Albrecht said that the loss of human and animal health can be related directly to the soil. That was over 100 years ago. The situation has deteriorated even further in the ensuing 100 years. And given the poor health of our soils, which I think most of you will agree, it's hardly surprising that more Americans are dying from a poor diet than any other factor, because you are what you eat. Now, part of the problem is poor food choices, but even those trying to eat good food are not getting the minerals and trace elements that they need. So agriculture is supposedly about food. I realise that in this country a lot of corn, for example, goes into other avenues like ethanol production, but basically we've always thought of farming as being a food production system, and there is something fundamentally wrong with that food, because the nutritional value of today's food is lower than at any point in history. Despite all the technology that we have, we are producing food that really doesn't have the minerals and trace elements in it that it should. We'd have to eat twice as much meat, 3 times as much fruit, and 4 to 5 times as many vegetables just to get the same amount of minerals as would have been available in those same foods in 1940. I have lots of data on that I'm not going to go through this morning because I have a short amount of time, but you will find it on my website, and it's all published in peer-reviewed international scientific journals. So what has been the effect of this mineral depletion on the plants themselves? Well, we're seeing increased plant susceptibility to pests and diseases, which in turn requires the application of insecticides and fungicides that absolutely would not be necessary if we had healthy plants. This reduces farmers' profits, and it's also adding unnecessary chemicals to the food chain, which is part of the problem that we're seeing with our autoimmune disorders. So just to go back to that figure again and look at that really large blue area, it's only farmers that are suffering as a result of this. Agribusiness in general is doing very well, thank you very much. So farmers are spending more and more on inputs, but the situation keeps getting worse and worse. So the official explanation for this lack of nutrient density in our food is the dilution effect. People will tell you, well, yield has increased. Over the decades, yields of various crops have definitely increased, so therefore mineral levels theoretically fall. If you produce twice as much, we're told, then it will have half the amount in it. But we don't actually see that in crops grown in biologically active soils. We see the opposite. There are farmers around the world who are producing more. Their yields are high, their productivity is great, their resilience is fantastic. In lower rainfall or higher rainfall years, they're managing better than some of the other farmers. And then the food that they're producing is a very high nutrient density as well as being high yielding. Some of our farmers in Australia are now procuring markets, particularly in Asia, for nutrient dense food, which is being segregated. It's actually being kept now stored on farm so that it doesn't go into bulk storage and shipped directly to Asia, and they're prepared to pay a premium for that food. They're also paying a premium for food that doesn't contain nitrate, so grains that don't contain nitrate. And why, you would think, are they picking on nitrate? Like, why not be looking at insecticides, fungicides, glyphosate, whatever, the things that you would have imagined would have been the issue? And it's because the nitrate content of the grain is directly related to all of those other factors. If farmers can grow high mineral, well, they can't grow high mineral grain unless they're not using nitrogen fertiliser, so they have to use something else, a biostimulant, which I'll talk about later this afternoon. And those grains that don't have nitrate in them also don't have insecticides and fungicides, etc., because there's no need to apply them. The plant is able to defend itself. So people are now becoming interested in eating that nutrient-dense food because that is the solution to the autoimmune disorders that we're seeing across the world, not just in the United States. So dilution is not the cause, soil depletion is not the cause. A soil test will show you that in total those minerals and trace elements are still in the soil, but they're no longer in the plants. For some reason, plants are no longer able to acquire the minerals and trace elements that they need, even though they are there in the soil. So why is that? If we had time today, we could explore that and have a good discussion about what the reasons for that might be. But to answer that question in a short amount of time, we first have to ask several others, and that is, well, what is soil? Really, what is that stuff that you're using to produce this food, and by what processes does it form? Because when we understand what soil is and how it forms, then we can see where we've gone down the wrong track and how we may be able to reverse that, so that we can have the kind of nutrient density in our food that we would like to see. We can start restoring soil health in terms of its carbon content and its soil structure, and we can grow crops that are going to be far more resilient in the face of the climatic extremes that we're now facing, and also be more resistant to pests and diseases, which is what we want in farming, because that means when we grow those kinds of crops that our input costs will go down, and we can start having a green line that very closely follows that blue line. So what is soil, and where does it sit in the hierarchy of life? Well, how often have you heard the phrase, the soil is the foundation of everything? It's probably said quite often at these kinds of conferences. Certainly if you go to a soil science symposium, just about everybody will be getting up and saying soil is the foundation of everything. I used to say it myself. It's one of my favourite sayings. So if we looked at that very simplistically, this is how we all tend to view soil, I'm sure, and certainly for most of my life I have viewed it this way, that you have soil at the bottom of this pyramid. And plants, well, they grow in soil, don't they? And then your animals, if you have livestock, they eat those plants that grow in soil. And then when our crops and pastures aren't performing as we'd like, then we want to add something to the soil to fix it. So if this is the construct, if this is the way that we see the world, our farming agricultural world, if our plants aren't performing as we'd like, our crops aren't producing as we'd like, what's the first thing we do? We go and take a soil sample, send it off to the lab, which will analyse the soil and come back with a report that says the soil's lacking in nitrogen, or it's lacking in phosphorus or potassium or sulphur or calcium or magnesium or something, and you have to add that to the soil to fix it. Right? Isn't that the construct that we've all been told? This is how we see the world, and this is how we deal with the issues if we think our plants or our animals aren't performing as we'd like. It's been our go-to. It's like test the soil, see what's missing. But what if soil is not the base of the pyramid of life? Have we been directing our energies to the wrong thing? And when you look at the input costs that we have and how much reliance we have on that model, take a soil test, add something, and then if your plants still have issues with pests or diseases, then you add other things, the insecticides, the fungicides. Is it because we've actually been looking at soil in the wrong way that we've been making those decisions that aren't leading us in the direction where we need to go? And I'm sure all of you in this room would agree that there could be better ways that we could go that are going to be much more productive and profitable for you, and also better for the environment and for the consumers of your food. So that leads us right back to the question, well, what is soil? How many of you think about that out there when you're working with your soil? What is that stuff? If I had a bucket of soil here, what would it have in it? What is it made of? And what makes it work? We haven't got time to go into that today, as to actually discuss what would be in that bucket and what would be the things that would actually make that productive for you as a farmer. So if we look at the definition of soil, we find that it's weathered rock materials of sand, silt and clay. Depending on what kind of soil you have, it's going to probably have had different origins depending where in the world you are. Sometimes it's going to be very sandy, sometimes it's going to be almost pure clay, or it's going to be somewhere in between, and that's what's called your soil texture. But it's not actually soil unless it's been in contact with plant roots. And why are plant roots important? Well, if you go somewhere in the world where there are no plants because the environment is too hostile for plants to grow in, if it's too cold, it's too hot, it's too dry, It's 2-something, so you could go to the top of a mountain above the tree line where there's no plants growing, and you'll find weathered rock materials, but you won't find any topsoil. You could go to the Sahara Desert where it's too hot for plants to grow, you'll find a whole heap of sand, you won't find any topsoil. And we intuitively kind of know that, but we need to wind back and look the other way. Well, where plants have grown the best over time, that's where most of the topsoil is. So if you look here in the United States, your prairies are have been your best topsoil, because you had good deep soils grown where there was a variety of plants, hundreds of different kinds of ground cover plants, warm season plants, cool season plants that were able to grow at any time of the year that it rained. There was something there that was green, that was actively growing, and very, very deep plant roots that went down, in metric terms, several metres, building beautiful deep topsoil. If you take those plants away for any length of time, that soil deteriorates, and the longer it goes without plants, the more it deteriorates. So not only do we have to have plant roots there in the past to build what we consider now to be topsoil, but we need to keep plants there to maintain the health of that soil. You cannot have healthy, fertile, productive topsoil without actively growing green plants and their roots. And we need to look at what kinds of roots they are, how deep they are, how many different sorts there are. So if we look at this like to use an illustration, the soil that is sitting there underneath that grass has over hundreds of years probably been actually built by the presence of that grass plant or other grass plants like it in that grassland situation, because green plants are able to photosynthesize. So they're going to capture carbon dioxide from the air, they're going to utilise light energy and water from the soil to transform carbon dioxide, water and light into biochemical energy in the form of glucose mainly. And then that energy can be moved around inside the plant. It can use some of it to build itself, so it can join the carbon atoms that it's produced during photosynthesis, during the production of that glucose, to make cellulose, which is what its leaves are made from, and to produce the starches and things that will be in the grain, and the lignin that's going to be in the roots, and the waxes and the oils, and all of its plant protection compounds that it will use to defend itself from insects and other diseases. So in that process, it is also going to be exuding carbon from its roots to build topsoil. Now you would ask, why would a plant be bothering to do that? Why would it? This photograph here shows you what it looks like when plants are actively exuding carbon from their roots. A lot of crop plants don't actually look like that, and I'm going to explain why, because this is the process that is going to build topsoil and maintain topsoil, and if your plant roots don't look like this, then it's not happening in your crops. Now, what's going on there is that the plant, in order to acquire the minerals and trace elements that it needs from soil, has to feed the biology around its roots. The plant has to have constant exudation of energy, because the things that live in the soil that will make minerals and trace elements available to plants, they are living and they need energy too. They're going to get their energy from the light, that in the same way that plants utilise light, transform it to biochemical energy in the process of photosynthesis. That energy, which we also use, we're utilising light energy when we eat plants, or we eat animals that have eaten plants, where basically the plant converted light energy to biochemical energy, and then we consume that energy in the form of food to run our bodies. Well, the microbes that live around plant roots, they also need energy to perform the work of making minerals and trace elements available. So when there's lots of energy coming out of plant roots, you'll see what are called rhizosheaths around the roots, which is the hotspot of microbial activity, and there's lots and lots of life, trillions of different kinds of, trillions in numbers I mean, of microbes, and thousands of different kinds of microbes living in that rhizosheath. The rhizosphere is the area around a plant root, and a rhizosheath is when you have soil sticking around the roots, which is what we want to see for all of our plants. And if we take high magnification, if we look really closely at what's happening inside that rhizosheath, not that one in particular, but just in a healthy rhizosheath, the plant root is to the left and the soil particles are to the right, and what you're seeing in that gap between the plant and the soil are the hyphae of mycorrhizal fungi and trichoderma and all kinds of saprotrophic fungi that are feeding off the sugars that come out of the plant roots, producing sticky substances to hold all that soil around the plant root. And there are also millions of different kinds of, or millions in number, I should say, of bacteria and archaea and yeast and all kinds of things living in that environment. So it's a very food-rich, energy-rich, very protected environment because the rhiza sheath maintains moisture in there, and in that's the factory that actually processes all the things that your plant needs. The plant can also fix all of the nitrogen that it needs in a rhiza sheath. So it doesn't matter what kind of a plant it is, you don't have to have legumes to fix nitrogen. If your cereals, for example, or whatever it is, have produced rhiza sheaths, then they will be fixing nitrogen. If we just move back a little bit in slightly lower magnification, this is in a sandy soil in Western Australia where we grow a lot of our wheat. You can't actually see the roots because that's a kind of a close-up of you can see the fungal hyphae holding all the particles together and pulling the soil around plant roots. If we look at this like in a 3D kind of just a graphic of it, the one on your left is compacted soil that doesn't have good aggregates that have been formed by plant roots, and the one on the right is where the soil particles have been pulled together by the glues and gums from the microbes supported by plants to form good aggregates and therefore lots of pore space in that soil, where water can infiltrate easily, where air can infiltrate easily, and if the roots are going to support microbes that can fix nitrogen, then we have to have lots of atmosphere, lots of air being able to get into that soil. So good soil structure is important for that because the atmosphere is 78% nitrogen, and that's the way plants have obtained their nitrogen for millennia. And if you look around at the green plants, which aren't there at the moment because everything's covered in snow, but in springtime when you do look out and see green plants, most of the ones that you see like along the sides of the road or in people's gardens where they're not using nitrogen, they're green, but no one's putting nitrogen on them. So even the lawn is getting all the nitrogen that it needs from the atmosphere. If we don't have good soil structure, I'm sure you're all aware of what happens, and I saw examples of this yesterday, although what I saw yesterday was covered in snow. But the one on the right, obviously poor soil structure, water lying on the soil surface. It's not able to infiltrate as it is with the one on the left. So if we look in a little bit more detail now as to what is actually going on biochemically inside those rhiza sheaths, this is a diagram that was drawn by Rudy Garcia, who's within RCS in New Mexico, and there's a lot of detail in there, and I probably don't have time to go into that detail now, but again, this is on my website, and you can read all about it there. There's an article called Nitrogen, the Double-Edged Sword, which has this diagram in it. But the green coming down through the centre of that is a fine feeder root, so carbon exudation is more prolific around young, actively growing roots and around young plants, and then the green bits coming off horizontally from that are root hairs, which are too fine for us to see as a general rule with the naked eye. So inside that aggregate you have microaggregates, orange areas that are formed by bacteria pulling soil particles together. The macroaggregate, the blue areas, formed by fungi. There are fungal hyphae coming out of that plant root which pull all the soil particles together, and so it's basically it's bioengineering. It's bacteria and fungi in the soil utilising energy from the plant to build new topsoil. That's how new topsoil forms, and that's the factory that it forms in. So what is it that we want to see happening inside those rhiza sheaths and macroaggregates? We want to see the plants forming humus, because this is going to be the holy grail for your soil. Humus has very high cation exchange capacity and very high water holding capacity, and it is the primary builder of soil structure. So this is what is going to make it much easier for crops to grow and for them to be much more resilient in the face of climatic extremes or in the face of biotic stresses from pests and diseases, because they'll be able to obtain all the nutrients and things that they need. Humus is about 60% carbon, 6 to 8% nitrogen, and a little bit of phosphorus and sulphur. It's always in those same ratios. It doesn't matter what kind of soil or where in the world it's built, it always has the same ratio of those components. That adds to about 70%. The other 30% are minerals in the soil. So it's formed in situ, and it's an organo-mineral complex that there's a combination of carbon and nitrogen, both of which are fixed biologically. And if nitrogen isn't fixed biologically, then carbon cannot be sequestered in a stable form. So if we add it as inorganic nitrogen, it will actually reverse this process and destabilise the carbon in your soil. So if we look at the humic molecule, it looks something like that. You can just see that, well, basically, in its simplest forms, we've just got carbon, oxygen, hydrogen, nitrogen, all joined together by microbes. Microbes have created those polymers. The humic polymer is microbial, and the energy for joining those atoms together comes from the plant, comes from photosynthesis. So the more photosynthesis we have and the less chemicals we're using, the more soil we can build, and the more profitable and productive and resilient farming can be, because this is actually the thing that underpins the processes that you need on your farm to support all the things that are going to make it easier for you. The liquid carbon pathway is what I'm describing. As I said, it starts with photosynthesis. We have to have translocation of the carbon compounds formed in the leaves down into the roots. We have to have aggregate formation around the roots, and then humification. So there are 4 steps involved in this process, and anything can interrupt those steps at any point along the way. For example, if we use fungicides on our seed or apply them to our plants, we're basically going to disrupt all the things that those fungal hyphae can do in terms of pulling soil particles together and moving things around in the soil. So steps 1 and 2 require the presence of actively growing green plants, and steps 3 and 4 require a diversity of beneficial soil microbes. So this fertile, humus-rich topsoil that we would all like to have on our farms is a product. It's a product of photosynthesis and microbial resynthesis, and it's a product that you can, it's something that you can produce in a relatively small amount of time on your farms. Even though soils we know have been there for a long time, we can rebuild topsoil incredibly quickly, and I'll be talking about that after lunch. So it's photosynthesis, not soil, that forms the base of the pyramid of life. So our pyramid looks like this. We have photosynthesis on the bottom, which requires green plants, light, carbon dioxide and water, the basic ingredients. Roots and their associated microbes. If we were out in the field, we'd be looking at the roots. How deep are they? How vigorous are they? Do they have riser sheaths? How many different kinds of roots are there? And when we get a great diversity there and everything functioning effectively, then we can build topsoil. And as I said, we can build it quite rapidly. So that word photosynthesis basically means photo means light, synthesis is putting together. So the word means making life from light. And it's a very, very powerful thing that you can implement on your farm with cover crops and diverse cover crops, for example, to quite rapidly build topsoil. But you also have to be aware of the things that interrupt that process, because you can have cover crops and still not build soil if you're interrupting the process with high analysis chemicals. So if we just look historically at what's happened on the major continents over time since European settlement, this is a diagram that was presented to the Food and Agriculture Conference in Rome last year, not by me, but it's in one of their publications. And you see there on the left we have healthy soil, as it was when the prairies were intact, as it was when our native grasslands were intact in Australia, and the grasslands, the savannas were intact in southern Africa, etc., etc., and the pampas grasslands in Argentina. It's not just the United States, it's around the world. We have seen this change from where the ecosystem was healthy, was functioning, was building topsoil and maintaining topsoil, and then the next frame, as you go to the right, it says at the bottom, NPP decrease. That's net primary production. That means there's less biomass on the soil surface. How did we get less biomass on the soil surface? Well, we either overgrazed it, or we burned it, or we ploughed it, or we sprayed it out, or we've got all these amazing ways that we keep getting rid of biomass. We don't want plants, for whatever reason, to grow there. We think it looks great if it's bare. I don't know where that came from, but what we haven't thought about is that if you have a decrease in the amount of net primary production compared to what it was prior to European settlement, then the next frame is SOC decrease. That's soil organic carbon. If you have less things growing on the soil surface, you will have less carbon in the soil. And when you have less carbon in the soil, that takes you to the fourth frame, which is soil moisture decrease, which is probably not such a huge issue in Ohio from what I can gather. You'd probably like it to be, for it to be going off up into the atmosphere and evapotranspiration to be increasing, as that figure shows. But in most other parts of the world, and in fact most other parts of the United States, water is the limiting factor for production, and people would really be preferring to keep more moisture in your soil. But probably the big issue for you here in Ohio is we go back to the third frame, which is soil organic carbon decrease, because if your organic carbon is going down, you're going to have compaction issues, you're going to have water laying on the surface of the soil, and you're going to have all kinds of pests and diseases issues as well, because it's carbon that is actually going to drive the system, and anything that's going to reduce that is not a good thing. In some parts of the United States we get the heat dome effect, where we have that kind of environment. If you look at the fourth frame there, where you've got all that massive amount of heat rising from the surface, actually increases temperature regionally. Jonathan Cobb, who I stayed with last week in Texas, has measured on a day when the ambient temperature was 105 degrees, the soil surface of a bare field was 155. So what that means is that you have air that's 105 degrees, it's heating up on that bare soil surface and rising because hot air rises. Then the other air at 105 comes in and heats to 155 and rises. More air comes in, heats up. You're actually generating heat and creating a heat dome. Under a warm season multi-species cover, the soil surface was 77 degrees. But even if you had brown plants there, like even if you had some kind of crop residues or something that was covering the soil surface and maintaining the ambient temperature at 105 degrees, you're not going to get a heat dome effect. But when you've got bare soil and you've got hot air rising, heating up and rising, and they are on black soils there, it definitely creates a heat dome. We have heat dome effects in Australia, and that's what's happening to us right at the moment. That's why it was 120 degrees in Australia recently. We've had a massive heat wave because we have lots and lots of bare ground that we did not have before. So the presence of green plants is the most important factor for climatic stability, but it's also the most important factor for soil health. How long have I got, Randall? 5 minutes. Oh my goodness. Okay. Just very, very quickly, that's a drought year in Australia. There's crop failure there except for where there was a fence. That farmer has been no-till for 30 years. There's been no soil disturbance. It was a grassland prior to that, never ever been opened up. But we have wheat there for 5 months of the year, and then over the hot months, 7 hot months of summer, bare ground, maintained with a chemical fallow. So he's done that for 30 years. This year he just took the fence line out. The fence had weeds growing along it that were capable of responding to rainfall at any time of the year, so there was always something green. There was a big diversity of plants there. There is a huge difference in that soil. Never been cultivated, but where there's been plants growing year-round compared to where there's only been plants for 5 months of the year, look at the difference in the growth. That crop that is growing where the fence line was is not showing any indications of moisture stress. So we have actually created a lot of the issues that we're seeing with our soil by having it bare for a long period of the time. So it's because these actively grown green plants actually support the microbes. It's the microbes that are important, and I'll talk about that this afternoon, that create this well-structured, friable topsoil that we want. So photosynthesis and plant root exudates are now recognised scientifically in international peer-reviewed journals as constituting the primary pathway for soil building. So why is this liquid carbon different to what we call organic matter? Why is it different to returning crop residues to the soil or adding manure to the soil or something else that is actually organic matter? What's the difference between liquid carbon? Well, there's 2 pathways for carbon in the soil, and there's the well-known decomposition pathway where you have something that starts off as biomass like residues or plant roots or animal manures, and then there's the liquid carbon pathway where we have active carbon exuding from roots of green plants. The decomposition pathway still starts with photosynthesis and biomass production, but then all of that material decomposes and goes back to being CO2, or nearly all of it, probably around 98% of it. If you see things like this in the soil, that's a really good sign. That's saprotrophic fungi that are breaking down organic matter, and that's fungal mycelium. That's great. I mean, I'm not saying this process is not good for soil. If you see that, it's fantastic. And we know mulch is great. Decomposing organic matter helps to buffer soil temperatures and maintain moisture, but the soil on the left, that's just decomposing organic matter, will go to be the soil on the right. It cannot stay as it is because decomposition is an active process It's a catabolic process of breaking things down. The microbes that are involved in decomposition keep on decomposing until there's nothing left there. The other process, the liquid carbon pathway, is an anabolic process, a building up process. It's where very simple carbon compounds come out of plant roots and are polymerised by microbes into complex carbon compounds such as humus, which are very stable in the soil. And if we put those two pathways together, you'll see there's a plant in the middle there, and the direct line that's coming down from underneath that is plant root exudates that are leading down to stable soil carbon at the bottom. Over on the left, you'll see there's some leaf litter, and then there's root litter as well that often have lignin, sometimes cellulose, hemicellulose, complex carbon compounds that the microbes that are involved in breaking those things down do produce metabolites, particularly fungal metabolites, that are important to feeding into the humification process as well. So both of those pathways are important, but the liquid carbon pathway is the primary pathway. We now know that plant root inputs can build soil carbon 5 to 30 times faster than carbon derived from above ground biomass. So when we see people producing huge amounts of soil carbon in a very short amount of time, it doesn't fit the standard model that's related to organic matter. So people will say, well, if you add this many tonnes of organic matter, you're only going to end up with this much left in the soil. So how could you build this much soil carbon? There's disputes raging all of the time about, well, you know, how did Gabe Brown, for example, build all that soil carbon? Because you'd have to add so many tonnes of organic matter that it wouldn't be possible. Well, he's not building it through the decomposition pathway. He's building it through the liquid carbon pathway. And that then answers that problem because it can be 30 times faster. And soil organic carbon is that one single measurable factor that tells us most about soil health. I think I'm probably right out of time now. So I'm just going to skip over these and just tell you that just this one, statistics show that 50% of the world's cropland is bare in any 12-month period. Actually, I just need to go back. 30% of the world's cropland has been abandoned in the last 40 years due to soil decline, and it continues to be abandoned at the rate of 25 million acres a year, and that's all again from international peer-reviewed scientific journals. And why? Well, because it's bare. So it doesn't matter what, you know, cultivated or zero-tilled. If there's no green plants there, then you're still not going to be building soil carbon. So I think I'm going to have to leave it there.